Okay.
That's what she said.
Let's go on then to where we stopped. So is everything clear till now? Up to this point, did you get everything, or any questions, any uncertainties? Nothing? So this means that either you understood everything or nothing. I hope you understood everything. All right. So we were talking about projections. That is nothing but, in this case, putting 3D points onto the 2D plane, like in case of the maps. Here we have some example, like just list of the ways of doing that. For example, planar or flat, spherical, cylindrical, cube, or shrink wrap. Yeah, before I go to the next slide, let me explain. The shrink wrap is actually when we shrink our texture the way that it fits best to our model, and then wrap it as densely as possible so that we could cover everything and we could very good correspondence between texture elements and this model elements, model objects. So this is wrapping whatever, like the word says, like literally wrapping our texture around the object as close and as good as possible. Well, some examples here. I want your input. Can you guess which of them are made of which kind of projection? Any ideas? Guess. Try to guess. Maybe hint would be that the ones in the column are result of the same type of projection. So these ones are similar, those and those ones are similar. So the ones in column-wise, we have identical projection. Type of projection, not the geometry or texture necessarily. Yeah?
The one on the left looks like the flat projection, because on the flat surface it maps pretty well, but on the edges it all falls apart.
Yeah, that's true. Yeah, exactly. So what it actually does is that it projects from only one plane. For example, if I have this bottle and I have this texture, I don't wrap it like this, but what I do is just like project this, like this is a texture, this is an object. I project this from this plane, so just 2D information is gone. Like, for example, all points across this point get this color, but we have no information from the top or from the bottom. So we just have this plane coming this way. So yeah, here, for example, we have top, and here we have this way, and this way there is another texture, and so on. Yeah, any guess about this one? That was very good cue, actually. Very good guess, like cue to identify. Can you use that cue for other? Yeah.
For the balls, we have ball, cube, and then cylindrical projection, I think. Seems like it.
Which one is cylindrical?
The up to the right. Top right. Ball.
Which one? Which one? If you here it's very clear, actually. Like here, well, on the sphere it's very good also, but here, if you look at the cube near the pole, you have something like the spherical pole. So this is spherical, I think. This one should be cylinder, and this one is cube. And if you have a look at the cube, it has like very good projection from all the sides. Like if I'll go through them one by one. Yeah, planar is yeah, what I have explained. You just project from one plane, not caring about other dimensions, and you have, for example, this plane projected onto those ones just like from this side. So this is example of the cylindrical. You have your object and you wrap it around like a cylinder. You actually put it in the cylinder, and then you map the points on the surface of the cylinder. So the spherical is a bit different, because instead of having it like a cylinder, you have this wrapped around like a ball. So instead of having just those ones parallel wrapped around, it's difficult for this one. But for example, let's say about mouse, so you have this like a sphere around this one, and then you map again, and that's why it was so good and one-to-one for the sphere, for the rightmost part. And the cube is that you have just 6 facets, and you have your object, and you actually, I think this is not explicitly mentioned in the literature, but I think this is combination of 6 planar projections. So you have 6 facets, and you do them from each direction, like from all the 4 sides, from the top and bottom. You project each of the facets onto the object. Like it's very apparent here. For example, these colors come from this side, this comes from this one, top comes from this texture projected, and this one comes from this one. So yeah, it's actually a combination of 6 planar projections from all directions. Yeah, this a few words about projections. And now one very important problem. Till now we somehow assumed, if not explicitly, that the texture is larger than the surface we have to project it on. So for example, this is a texture, I have the mouse, and I have many ways of mapping these coordinates onto this one here. But imagine that texture is small, like for instance like this big, and I want to project this texture onto my phone, right? So when the texture is smaller than the actual surface we want to project it on, so what do? There are like 2 S and T coordinates, 2 directions. I will show you like what do they do, and there are like several ways of doing that. The simplest way is to repeat it. So this is our texture map, and we want to put it on this window, but this is smaller than the window. So one option is just like repeat it and put it many times. Another way of doing that, it depends on the application completely, is plan. That is nothing but taking the very last available pixel on the texture and stretching it to the very end of the surface we are projecting. So this one is actually the value of the last pixel stretched all the way to this side, and this one is the last pixels of the sky stretched to that direction. And what those S and T coordinates do is that in which direction we want to that, because like here you have GL text parameter, you have GL texture 2D parameter, and then you do like, you have 2 operations. GL texture wrap in S direction in one axis, and then wrap in T direction in another axis. And then we select the methodology, repeat, and this leads to this one, the left one. So we like what this T and S do is that once we said that we want to do it in one dimension, and then we said we want to do it in other dimension as well. And here are other examples. We can do a mirrored repeat, which means that instead of copying this and pasting as it is, we just take the mirror. For example, this kitten is mirrored in this way, it's mirrored in this direction, in this direction, and this one is also mirrored across this point. So it just repeat, but instead of having the same one, it just opposite. Yeah, clamp to edge is that we just stretch this to the edges, and clamp to border is that we just select the border and just keep it like this. So like the border colors are kept for the rest of the surface. So those are some of the approaches to overcome the problem when we can't cover the whole surface with just like our texture. But there is another significant problem, and this problem is that when you place your triangle, let's make a triangle. So you have texture coordinate system, you have this modeling UV space where you're putting your model elements onto the texture, and you have actually image coordinate system in X and Y. And what you do is you take the triangle from this cube, for example, and you want to put it on the texture. But the problem is that these vertices, so we have some coordinate for this one, but these vertices do not exactly hit, it's very unlikely to hit like the coordinates and points of this texture. So we have some offset. For example, if it's 3, 1, 1, this might fall on 2.02, something like, not with the integer coordinate. So in order to calculate that values, there are several approaches, and that leads to the artifacts, because we don't have clear mapping from point to texture point. So what kind of solutions can exist for that one? Like, first of all, this is a flooring function. When we just imagine that this was color for this one, it's not the perfect image, but if we have this color in this area, and flooring function is that we just round, we just discard the non-integer part, and we take the integer, so we come to this vertex, and we take values from this vertex of the texture, and all this area is put to this vertex value. Another approach can be nearest neighbor. So in this space, we locate which texture vertex is closest one. So this is a triangle vertex of our model, and we want to match each to the vertex of the texture. So how to do that? According to this approach, we should select just a nearest point, and we take that one. Another more, but this one can also lead to the artifacts, because we disregard the possible impact of this one or this one. And another point can be by linear interpolation, where we simply consider all those values, all those vertices around. We consider their values, and we calculate the value of this point considering all of them. So linear interpolation was just like, for example, if we want to interpolate between this vertex and this point and this point, we just have some weights depending on the distance to the vertex and put that one. Bilinear is its extension to 2 dimensions. So we have 2 dimensions considered, and taking the neighbors, taking their values, having some math, and coming up with their value that has impact from all the neighboring vertices. And it can be extended to 3 linear one in 3 dimensions. Yeah, this is a floor function. Yeah, another thing that is also a problem actually is that well, we have this texture here, but we can simply interpolate it like between those two. We can simply linear interpolate. When it's like a plane in front of the camera, that's okay. But imagine that you have this texture like this and you're looking from that point. Then the interpolation between those two won't be that logical because we have a perspective and yeah, so like these two, I'll show you on this example, like so we have the flat surface, but when we change the projection, when those texture elements go farther, they become smaller. When they're closer, they're larger. So if we interpolate the same way, that might lead to some artifacts. So we have to consider the perspective. We have to consider which point are we looking from. Well, even though just simple linear interpolation is computationally fast, it can lead to this kind of artifact where, where we simply have the wrong interpolation because this one is calculated as it was like this, but it's actually in the space. Those elements are going farther, so we have to be careful about that, while those ones are closer and larger. So if interpolation here is done on this distance, it's like different on this because the perspective changes. And also like here, we can't simply do like this because it changes the direction. So what I want to mean here is that we have to consider the perspective and the offset that is introduced by the perspective. So there is no exactly that kind of match, but they move in a space. So these vertices should be considered in correlation with other ones as well. And yeah, considering perspective can solve some problems for us. Yeah, here is visualization. So instead of calculating this as orthogonal kind of bilinear, so taking the point from here, like you remember we had these straight lines. Here we had the straight lines when we want to find the points to calculate this value, but when we change the projection, we don't have the straight lines anymore. So we have to consider the perspective, like in this case. And in this case, we already calculate considering this kind of perspective. And anisotropic filtering is a good approach when we filtering is actually assumed to be done similarly in all directions, but when we change a perspective, we don't really consider all dimensions similarly. Like in this case, for example, this one gets very blurry because we just have like single point of view, and this is different angle, this is different angle, this is different angle, and if we calculate them as if we're like here, then it would lead to this blur and kind of hiding of the image. So what we do is that we have different kind of calculations depending on the perspective and direction, and we have more sharp image here. So this, like, I won't go into very deep details of this approach, but you can like Google and see the results, how different it makes the result when we have perspective of some kind of texture surface that spreads deeper into the space, or when we have 3 dimension and going into the depth. And yeah, here is an example of aliasing. Like aliasing is like when we have poor sampling, sometimes 2 signals won't become non-distinguishable, and that leads to some artifacts like jaggies of the line when we have like these kind of steps, or in audio it's lots like very famous, like very common artifact, or in textures, as you see here, like instead of keeping this structure clear, it becomes non-distinguishable because the sampling is not good enough. So some techniques to overcome that problem, like some anti-aliasing techniques. So does anyone know any of those techniques? Yeah?
I have put the limited into oversampling, but not much.
Okay. Yeah, Shannon-Nyquist sampling theory is like mostly for audios. What does it say? That it defines when we want to convert from analog signal into digitized one. It defines how many samples should we have on that discrete space to have this analog signal represented as good as possible, like not to lose significant information and not to get like very serious artifacts. So how many samples do we need in a discrete space to represent this continuous analog signal? And it says that yes, we should sample at least like twice as much samples as the highest frequency of this analog signal. Oversampling is, yeah, sampling more than it is. Like we'll see the example of our oversampling here when we put more samples than we had initially. Or would you add anything about oversampling if you? Yeah, jitter is just like moving the samples in like some, I think, random directions, just like moving them to different directions to make them like, to make the difference. And more sophisticated and very, very effective approach is providing preprocessed lower resolution imaging that we call MIP mapping. So it comes actually from both sides. Instead, like except for solving the aliasing problem, it is computationally very, very efficient, because imagine that we have this texture to put on the object, but the object is very, very far in the scene. We have to calculate all those points, but we don't see them because it's far and it's not very distinguishable. Imagine that it's so far that you see that as big as this one. So why do you need to calculate and run shader for all those points when you don't really see with your eyes, when you don't have enough aperture to distinguish all the points? So that makes computational very efficient, because we just decrease the number of points we want to process because it's far. We don't see that anyway, so let's discard that and just have a smaller number of points when it's far. And it solves also like anti-aliasing, because yeah, instead of having this one then shrunk and having uncertainty at one point, we have already something pre-calculated that we can simply project on that one. I will show you example on the next slide. And anisotropic sampling is also coming next. So here is the example of MIP mapping. So if we want to put this scene onto something that is very far, so we take different sizes. So it's actually, I think, decreases by size of 2, power of 2, I'm sorry. For instance, if we consider this 512 by 512, this should be 256, this should be 128, and so on. And we have these kind of different textures. And depending on where our model is located in this scene, whether it's far from the observation point or whether it's close, we refer to different maps to be projected on them. So we call them MIP maps. So here is another example of a MIP map. And if we get back to anisotropic filtering, actually these MIP maps can be projected on the object when they are like straight ahead from the observer, but we can't really put, for example, this one to something that is in an angle from the observation point, right? So to make it clear how anisotropic filtering worked, it's just considering the observation angle and the distance. So that how would MIP maps change if we take the projection and perspective into account, different perspectives. And where was that one? Oh no, this was anisotropic filtering. I'm sorry, this is a wrong title. So this is anisotropic filtering. What anisotropic sampling does is that we don't always necessarily need to sample equally in all directions. I will change this title. This is anisotropic filtering, and it should be slightly about sampling. So yeah, we don't necessarily need to sample equally in all directions. So it depends again on the viewing angle, and we might sample more densely or more sparsely depending on the angle and direction we're interested in. So here is a example of oversampling, like instead of taking a single sample per pixel, we put several of them, but only when there is uncertainty. So when there is an uncertainty, those ones that are in between also come into the play. So for example, if we didn't have these samples and we had just those points, then it would create artifacts because of the offset between those points and this triangle. While when we have dense sampling, we can have better matches to the vertices of the texture and the model put onto the texture. Yeah, and this is example of jittering, when we just like, instead of putting them in a logical order and some kind of pattern, we just move them a bit to have less uncertainty, because if we had, like, for example, those two here, or like those two here, then it would be offset between the two, but when we move this one, then it decreases uncertainty because one of them is closer to the actual triangle. And yeah, mapping, as I said here, we have this like by power of 2, so we can't have MIP maps for any possible size. That would be also very costly, and that would evaporate its advantage of being efficient. So we can't have like infinite number of possible sizes of the MIP map. So what we do here is that when we have our model, we have to find the nearest MIP map and calculate using that. For example, GL nearest MIP map uses a MIP map that is most closely in terms of size to our model, and then it just uses nearest neighbor interpolation for sampling. So nearest neighbor was just in that space taking the closest possible point, while GL linear MIP map does the same, but instead of taking nearest neighbor directly, it takes linear interpolation. And those two parameters, instead of taking one, the closest possible MIP map by size, they take two of them and calculate between those two to have the proper values. Like here are some examples. So when we have this box, and then it comes like this is our model, and this is when it goes far, and we have like several, or in this case it's magnified the other way around. We have this one and we zoom it in, so we magnify it, and we have several options. Like, I don't think you see much difference, but you should see the difference on your screens. So this is one methodology when we take the nearest neighbor, and when we take the linear interpolation, it becomes smoother, because instead of just cutting and taking the point whichever is closest, we consider points, other points as well that are in the nearest vicinity. And yeah, this does linear map nearest, that uses, I think, yeah, the third one uses linear interpolation using one MIP map, and the second one uses interpolation between the two MIP maps. And we have, yeah, either magnification or minification. Oh, here is the slide about anisotropic sampling. I should have put it a bit earlier. Yeah, anisotropic sampling, this is what I was talking about. So when we move in this, so it depends on the angle, like when we move in the space, the change in all directions is not the same. It depends on our angle of observation, it depends on the perspective. So in order to have the correct and sharper and better representation, we should consider the directions here, like yeah. Yeah, so like in the observation angle that should be sharpest, we use a full texture instead of decreasing and squeezing it. That's a key idea, I think. Yeah. That's not the focus of this lecture anyways. Yeah, let's go on. Yeah, filters of magnifying and minifying. This is actually nothing but zooming when we want to scale it. So when we want to either use one scale of the texture elements or another scale because of the distance from the observation point to the model. Yeah, we have this magnification filters, and then we have again like this kind of calculation depending on the nearest possible MIP maps, like here, like those ones. So for example, the size of our model is between this one and this one. It does not match either of them perfectly. So what we can do is like either take this one if it's closer to this one and calculate the vertex values by nearest neighbor calculation of this one, or linear interpolation, or we can consider both of them. So take two closest MIP maps. That's the idea of that. We have this one. And yeah, I think this OpenGL implementation is the same as on the previous slide. So we have texture parameter, and then we indicate filter parameter, so to identify the scale, whether we magnify or minify, and then we pass a parameter to identify which methodology do we want to use to interpolate or come up with the actual value based on our MIP maps. Because the reason we need all of those is that our size hardly ever matches actual MIP map sizes, so we have to be flexible to consider that. This is it. Yeah, and till now I have spoken. How much time do you have? Yeah, I think I can go very quickly through them. So till now I have spoken only about colors as a result of texture. So we have some texture, we take this value and put it into the corresponding pixel of that model. But it's not only putting colorimetric information, like textures can be used for bump mapping, normal mapping, that creates perception of 3 dimensions on the surface, or environment mapping, and it can be procedural, like I have shown example of sinusoidal, or like we can even use noise to present some amount of randomness. So if you watch the video I was talking about, there is a very good example where they introduce some randomness of the values due to render the marble, because you can't always predict structures with the marble texture. So you put some randomness, some amount of randomness, not complete randomness, to get this kind of realistic representation. So if you have a look at this wall, it's not really predictable, right? It's somewhat regular, but somewhat random as well. So this controlled randomness is used to present these kind of materials. And just to go through the examples where textures are used, like it can be used for blending. For example, when we have two different surfaces, and we have this transparency alpha parameter. We can mix the color or blend the color of the two to get the average color, or we can have illumination, and we will get back to this when we will talk about illumination and shading and stuff. Bump mapping is actually when we want to render the appearance, we consider like geometry, what is the incident angle of the light, what is the observation point, and what is a normal point to the normal to actual point. But using bump mapping, we move those normals, so we create shadows and highlights so that we have illusion of 3 dimensions. And normal mapping is actually having more numbers of normals corresponding to larger number of polygons or triangles, and then having them put to smaller number of elements and having the impression of 3 dimension, because we have several different normals like here. Yeah, band mapping is that we have this surface that looks very smooth. We take the height information from this map, so darker it is, lower the normal goes, and when we change the surface normals, it creates the shading and shadows, having the impression of this kind of hot hole on it. And the normal mapping is when we had the flat surface, we have these normals from the actual complex rough surface, and we put those normal informations to the flat one to consider in rendering process and get that shading information. This is the example of normal mapping. Distortion mapping is the one that actually alters the geometry. So here is a good example. So this is bump mapping. We have very flat surface, like normals are facing upwards, and if we want to have the impression of this roughness and irregularities on the surface, we simply move those normals, and when we calculate the color based on the illumination, we actually assume the geometry and get to this shadows, but it works pretty well. As you see, it has some impression of having rough surface. It's not smooth, but when we look at the silhouette, actual vertices remain at the same point. So even if we imagined moving this one and having this shadow, it remains at the same location. So if you look to the silhouette, it's like completely smooth, while the surface looks very rough and bumpy, right? So what displacement mapping does is that it actually moves those vertices up and down, so it moves those triangles, and we have more realistic representation. We have this kind of geometry of bumpiness on the surface. Environment mapping is very, very handy when you want to have reflection, when you have something very glossy, mirror-like object, and you want to reflect the environment. So you, for example, represent your room like a cube. You have like a cube projection. You fold, wrap it around your object and project, and you have environment reflected here, or environment reflected here. So actually this texture isn't part of the object, but it's coming from the environment. But the approach is the same, like you imagine it being a texture and you use this way. And nothing looks. So yeah, and camera. Yeah, so it looks towards the camera, and the trick is that if the axis is, you consider illumination axis, you consider observation axis, you consider normal, and you can actually control what part of the environment should be reflected at this area, and whatever area. So you can have more control on that mathematically. I have already talked about noises to have more realistic representation. And yeah, 3D textures. Carving, yeah, carving is actually called, it's more or less the same as the procedural approach. So instead of having the object and projecting the surface, you carve, so you calculate the values one by one, you follow, and it's like carving the stone, so values are found by some mathematical approaches in the 3D surface. And yeah, that's more or less it for this slide. And texture readback is a technique of reading the frame buffer, so whatever was visualized or displayed on the screen, reading it as a texture, and this gives us some flexibility in OpenGL. It gives us opportunity to evolve some effects on the scene and process whatever was visualized further as a texture, and apply all the manipulations we have for textures. And it's implemented in OpenGL since 1.1 version. Yeah, on the last part I was very fast because we were running out of time, but I think it's the general idea of texturing. I think it was more do you have any questions, or was it clear, or do you have like something that confused you a lot? Because I was like in the last part I was talking too much, didn't get much involvement from you, so just want to make sure that it's not necessary to get all the math and all the tiny details behind, because the good news is that today, like hardware and OpenGL do that for you. Like for example, perspectives are handled automatically. You don't need to explicitly calculate all the perspectives and stuff, but like you should be understanding what all those stuff are about. Yeah.
So with the camera technique there, I'm assuming that was kind of what was used in the like 2000 to 2010s-ish for reflections, where you or like stuff that can move in the environment isn't reflected. How do you do? Because more games now recently are doing, you know, actual dynamic reflections. How do you do those? Do you just have like a virtual camera, or?
Dynamic reflection, you mean when
so
it's
your player
changed?
character would be reflected, and stuff that moves in the scene is also reflected, that kind of stuff.
Like a mirror?
Yeah, like a more realistic mirror effect than just reflecting the environment.
I'm not sure, to be honest, but I think it will just project texture with some rate. So because like in this case, this environment is considered a texture, and you're projecting it on this one, right? And you have a movement of your character here, and you want it to be reflected here, right? So I think you have some, I'm not 100% sure, but intuitively it should project the new texture considering the character in it by some frame rate. Or do you have any input on that?
Oh, that sounds really reasonable.
Like the pictures, potentially.
Yeah. So actually what the movement of your character does is that it changes this texture, and then you project it again and again to have this smooth transition. Or maybe to make it computationally more efficient, you can just project it as a separate texture and keep all the rest, not to calculate all the environment again. I'm not really sure about this, how it is done. I think it depends on your implementation, how you do it in OpenGL. So, anyone, like, what have you, then I will ask the other way around. I won't ask what you didn't understand. What did you understand today? What was new or interesting, or what you will take home from today's lecture? Nothing?
The wrapping, I think, was pretty interesting. And nearest neighbors and all of that was interesting to go into those bit of details. Like, I have to review everything again because I'm looking at a bit of a slower pace.
Okay, yeah, there are the slides. There is very good video that will help a lot. And the good news is that you don't need textures necessarily for your first assignment. So even if you don't understand this, you can complete your first assignment without any problems. But if you're comfortable with that, and if you include your texture stuff in your assignment, it can be a bonus. So it's, yeah, but you will need this on the later stages for sure. So it's good to try to get into this. Yeah, thank you very much for your attention then, and see you on tomorrow's lab. And I hope like on the lab it will be more clear because it's about textures, and when you're doing it yourself it's easier to understand, I hope.
In the lab, will you just work on the assignment? Or?
No.
From the assignment, we'll be working with textures.
Yeah, so the lab is about textures tomorrow, but actually if you think we need a time for assignment and some questions and some instruction, we can have one lab dedicated to that. So if you guys want that, we can do that like next week maybe.
But the lab will be, if you do this lab, it will probably be tool that you can use for the assignment as well.
Yeah. Also for the assignment, you don't really need a camera, do you? Because it's just like one screen.
Yeah, that's true. But you should probably introduce the matrices still to sort of emulate the camera. Because if you don't, you might get problems with coordinates.
And you don't need any perspectives, so it's a 2D, like Pac-Man, wherever it's located is the same size, so it's not a 3D when it goes farther or this way.
Yes.
So yeah, it's, in that terms it's very simple, you have just one plane.
Yeah, but you might want to scale it to not work in the -1-to-1 dimensions.
Yeah. Yeah, in this case you don't need any scaling. So I hope that will be easy, and then it will be a good foundation for further assignments. Okay, thank you.